तेजस्विनावधीतमस्तु मा विद्विषावहै।
We have so far seen how to model in Verilog the combinational and sequential circuits, which are vital ingredients in any digital VLSI system design as such. And while the ultimate goal of the designer is to finally map it onto a device such as an FPGA or an ASIC. And this is possible only if you follow certain guidelines as such. And the popular guideline is follow the RTL coding. RTL stands for Register Transfer Logic Level as such. It's basically a synchronous circuit design as such, which you are already used to, and it signifies the data flow and how you process the data as such. And basically it is a synchronous design which should naturally run smoothly through simulation, then synthesis, and finally on place and route as such. In order to do this, you have to isolate the combinational and sequential circuit. Say, asynchronous fall under that combinational, which we have already seen earlier in our earlier lectures, and it has got to be separated out as we have already done in the previous class as such. And basically, RTL coding style is once again the same as synchronous design as such. You have a combinational circuit, and it can be any complex combination circuit, and then follow this with a register, registering this combinational output as such, and this may be an intermediate output as such, and then follow the same pattern successively, and this keeps going in this fashion, and data flows in this fashion naturally. It is normally referred to as a pipeline, which we will cover in depth later on when we deal with arithmetic circuits as such. And for the time being, this is enough if you know that RTL coding style is basically based on this separating out combinational as well as sequential circuits as such. And it basically consists of do's and don'ts, because this is supposed to be a guideline as such for the designers. And the common mistake that we do is to take a combinational output and feed it back, and this is detrimental in making a chip as such, because for example, if you say if you apply a 0 at the input here, and the combination might produce a 1 here, and then 1 being fed back, it keeps on rapidly switching from one state to another, and this will be uncontrollable as such, and thereby it will not work in the ultimate chip that you have designed. And furthermore, this may be rejected at the synthesis level itself. When you use the synthesis tool, this is not permitted. It will give warning or error message as such, and perhaps you can veto that and go along, but ultimately you will end up messing the whole design as such, for simple reason that your design will not work on the ASIC or FPGA that you have ultimately done. And that's the reason why we should stick on to this RTL coding guidelines as such, and without which you won't get a working chip as such. So the remedy for this is to break this feedback, and fortunately we have a synchronous approach for this that is depicted in the next slide as this. You have a flip-flop here, a D input flip-flop. So you break this earlier feedback as such here, and then pass it through a flip-flop, and you feed it to the D input, and there will be a system clock as such, which will be separately given to a clock input, and Q output is actually fed back. And here you see that whatever is the combination logic that you have inside, and which will produce this output, and this will be processed only when the system clock arrives, that is at the rising edge, if it is programmed for rising edge direction as such. And Q output is naturally delayed by 1 clock pulse, because this will take effect for the next iteration or whatever you call next processing only at the next clock pulse. So this is the price that you have to pay for breaking that combination logic, but this will result in a system which will work on the IC, whereas the other previous one will not work on the IC as such, and instantly it eliminates racing as well as glitches, which is normally present in asynchronous circuits, which we will see some of them later on. And this is the basic building block for asynchronous logic as such. And another mistake a designer does is gate the clock. This is very detrimental because it introduces skew in the clock. Skew is, if you have so many registers in your system, and the clock may arrive at one point of time here, and the same clock may arrive at different points of time, and owing to which you will be violating setup and hold times, which we have seen earlier what they are. And so the solution is once again break this gating of the clock and use it in this fashion. See, after all, what you want is to process the data for different conditions, and which you can do by using a mux like this, and your input data can be fed to one of the inputs, and you can interpose once again a register here, a D flip-flops here, the mux output being input to the D here, and once again a system clock separately routed to the clock input of flip-flop, and Q fed back to one of the inputs. This means D out is preserved when I0 is selected. The I0 can be selected if select is 0. If you want to select the actual input, which is the combinational or asynchronous input as such, select will have to be 1. That's clear from this picture. And to start with, this will be 1, and then this input will go through this path and land up into this register, which will be registered at the positive edge of the clock, and that will be stored here. And what is stored here will also be fed. This is a combinational path here, and this will once the select goes to 0, and then it will register the same input which was the previous output here. I think this is clear to you. And that's what it says. Logic must be incorporated in data input instead of gating the clock as such. And another point is, normally we would like to create pulses as such. And let us say we wish to create a pulse for a typical application, can be a timer, say photographic timer, and you want to produce a single push button activation, you want to simulate that. So you need a pulse of that kind. It can be either a single pulse or it can be long duration pulse. In the traditional way which designers normally do, which is an erroneous design practice as such, and will be to put different buffers in order to achieve this n times propagation delay. For example, TP is the propagation delay for each of this buffer, let us say. So finally you have a total delay of n into TP as such, and that is at this point. So this is inverted here and fed here in the gate, and also input is fed to this gate with a view to get this final output rising, positive pulse as such from the two inputs that we have here. And this input is basically from, as I said, a push button switch. Of course, you can't straight away have. You may have to have a proper debouncing, and that is implied here. And this output here is nothing but the same input after a delay as such. So this is the delay that you have. This delay is governed by the total number of buffers that you have, and that total delay appears at the output also. So if you combine these two in this fashion with note the bubble here, then our outcomes they decide a single pulse as such, a duration of which is governed by this n times TP. This is the traditional way, but this is unfortunately dependent upon the technology as such. For example, if you are in 0.65 micron technology, you might have produced, let us say, 100 units of time, say 100 millisecond or something. And now the technology has changed. Say currently it is on 0.09 micron technology, and naturally several fold is it has galloped maybe 8 to 10 times. So in which case, if you had not changed the design and but you have changed the device as such, then what will happen? The time delay that you have put here will not be achieved in the current technology. So it will be tenfold less, and which may not be enough to trigger some other mechanism that you might have envisaged at the point of designing. So with that's to say that it is technology dependent as such. So if it is so the way out here is, if you are interested in just creating a single pulse as such like this, so what you can do is you can have two flip-flops, and input is applied here, and that's this here, and it may appear at any point of time. So let us say it appears here, and there's a clock here, and we are going to reckon the whole thing on positive edge basis. And first flip-flop output is Q1, and naturally when rising edge clock is encountered here at this point of time, in is 0. So naturally the output is 0 here, and when it is subsequently it is 1 here, but this will be registered only at the positive edge of the clock, and that happens, it should have happened here, but owing to delay here between the clock and the Q output, this is naturally staggered a bit here. It is delayed a bit, and otherwise this is nothing other than the input itself here. And this in turn is applied to another flip-flop, and that output also can just have a look. That's also a delayed output of this particular Q1, and once again we get it here in this fashion. So ultimately we get a pulse like this, and this you notice that the actual width of this pulse is actually the width of this clock period. So except that there is a delay here owing to the delay between clock and Q, because internally there are circuits, and any gate means a delay in such as such. So that is what is getting reflected here finally, and this is how we solve for a single pulse if you desire just a single pulse to be created. And on the other hand, if you want high timings, say of the order of milliseconds or even seconds or even beyond, we have already seen one application called non-retrieval mono. That's what is put here. And this just to recollect what we have done earlier, it's based on a counter it was 8-bit wide as such, and you have had a setting also inbuilt there, and you can trigger this. This basically a mono shot, or you can view it as a timer as such. It can be triggered. That trigger is a starting of the delay as such. The desired delay is the same as in the previous case, except that this delay is now controlled by the set value that you have already programmed in, and it has a system reset as such and a system clock, and the simple waveform for this is when trigger is encountered at the rising edge of this, this delay also starts here, and this whatever is the set value here, you will get exactly in number of clock cycles as such. Had you set 255 inside, you will get exactly the same 255 clock cycles, and now you would notice, as in the previous case where a single pulse was produced, as well as in this particular example, it is technology independent. It is dependent only on the system clock as such. So you can see in the previous thing. So it is basically this final delay is based on the just on the clock and not on the technology. So even if technology changes, any future technology that would come, your design investment as such that you have made, had you adopted this one of the two schemes, is still preserved as such. So that's how we say it is a technology independent design as such. So a designer will have to keep all these do's and don'ts in his mind prior to actually designing any circuit as such. And another thing we talked of earlier is the glitch, which is an unwanted, uninvited guest that you would like to eliminate as such. So for example, this circuit gives a glitch as far as this combinational circuit is concerned, and a narrow pulse like this is known as a glitch. How it is produced, we'll just have a look. And, so these are all plain AND gates here with an inverter here, and then finally these two are ORed here, and then applied to a D flip-flop as such. Now let us consider a case wherein in 0 and in 1 both inputs are high. So in such a case, what will happen to this circuit? Let us have a look. Let us say the select goes from high to low, as in this case, and naturally after an inverter, this select bar will be the inverse of that. So here, and of course there's a delay here, and this gate delay is because of this inverter here, and if you see the output here at D1, what happened? It is nothing but ORing of this. Since IN0 and IN are 1 each, so whatever you apply here, that is select bar here and select here, will appear at the respective ends here, and this when ORed, you get basically this. It's precisely this rather, and this is caused because you can just see here, this is 1 and this is 0. So being an OR, 1 plus 0 is, or the other way, it is going to be 1, just as here also 0 1 here. So all through it will be 1, except for a small interval here. At this portion it is 0 here, and it is also 0 here. So this 0 will produce 0 here right at the D1, and that is how you get a glitch here, and this is contributed by this inverter as such. It's the propagation delay of the inverter which is responsible for creating this. Now if you had you processed this, say elsewhere without the flip-flop, what will happen? It may so happen when your circuit is sampling, it may sample at this point, and that is not the desired point. You wish to know the sample only when the actual say D1 is high, but you might sample here without your knowledge. So that will play havoc. Had you given this as a clock input for some other circuit, I don't have to tell what will be the implication there. And therefore it is very essential that we get rid of this glitch at all costs. And the way to do is put the flip-flop here. And what happens if there's a flip-flop here, naturally you can rest assured that there are other flip-flops from which other signals are coming, or It may even be an asynchronous, in which case you cannot directly put here. You need another flip-flop and then only process other asynchronous inputs as such, right, which we will see in the later slides. And here what is happening, this is happening, all this glitch will happen before this rising edge of the pulse. You should, total delay of this one, you should keep in mind, and then only select your frequency as such. Frequency operation is governed mainly by the total delay that you encounter in a combination circuit. And if you had taken this into account, then you can always condition that your whole circuit in such a fashion that whatever glitch that appears will be ignored, and the steady state value only is registered. For instance, in this particular case, it will be registered only here. And we make sure that all these unwanted signals, such as this glitch, occur prior to this positive edge, rising edge. Then you will be safe and not register the glitch, but only will register the steady state output here. And prior to this, you would have registered this here. And provided that is the logic that you have. And this is possible only if you have a synchronous circuit as such. And another thing normally a designer does is, as in a ripple counter, you give the Q output of one flip-flop into another and to clock off next. This is another practice which is not encouraged. In fact, it will create problems. For example, you may violate hold time. If you take one particular case, you will see that. So, for example, this is the clock, and D1, D2 are coming from external source, and suppose D1 changes somewhere here, arbitrarily we choose here, and D2 changes here, and simultaneously let us say this Q1 also changes. This is possible because D2 is not in our control, so it may appear at any point of time. So what prevents you from getting that change, D2 change, when there's a rising edge for this clock? You can't. So in such an event, so what will happen? You are actually violating the hold time. So actually these are all the steady state of the previous clock as such. So normally this will not pose any problem. And only here, that means it already satisfies the setup time. And what is going to be violated is the actual hold time. When clock rises, the data is not stable. As per the hold time, this data will have to be stable for at least a TH time as such. Beyond that, naturally this is violated, and you have no control over that. And so this is not to be, it has to be eliminated from your thing. The way out is, after all, you may decide to have a counter. Basically, we have already seen how to implement a counter, and that implementation actually conforms to the RTL coding as such. In fact, all that we have considered right from beginning conforms to the RTL coding style as such, and now what we are formalizing the need for following that style, and some of which we have already seen. Earlier we have seen how the basic RTL coding style will follow the pattern. As depicted in this figure. First combinational, then register that, and then follow it by another combinational, register, and so on. This is how data flows as such. So it flows from one point here, and then it flows to this, and then sets down here, and so on. It keeps on going stage after stage, and so it is the same pattern that we have followed there in that particular code which we have. We mentioned earlier that we need to separate out combination as well as sequential circuits, and here it gives one particular module as such. A module is you can regard it as a single file in which you need to follow certain pattern while coding it. What we have seen earlier was only piecemeal coding as such, and now it gives little more information here. For example, it says that what you are going to the code that you are going to put is a module as such. A module is something like a black box. You have a block diagram which you are already familiar. It will have an IOs, and that's precisely what you have here. So that block can be given a particular name, and the block itself we call it here as a module. And once you have a module, you should signal to the tool that is going to process further by another corresponding signal called end module. And note that there is no gap after end and module. It's a single word as such. So module, end module. This is a vital thing that you have to keep in mind. And once you have given identified it as a module, then you have to give a module name as such. For example, this is a model for RTL. So I'll name it as RTL underscore model. So this like this you may have several such modules, but it is illegal to nest modules within modules. I mean, nesting itself is putting a module within module. For example, I cannot say somewhere here before the end module call another module, say sequential module. I can't put another module. That is an illegal thing in Verilog coding as such. And once you identify the actual module as such, this is the module name as such. You then list the IOs here, and you can put it in any form that you want. IOs can be in any order that you like, and these are all separated by commas here. And this is nothing but a D flip-flop which we have already seen. Only thing is we point out here the need to separate out combinational as well as sequential circuit. So that's what we are doing here. And here you list all the inputs which happen to be D1, D2 and clock here, and you can put it like this or separate it out in different statement as such. So is the case with output, and you just list them. And we'll see more details when we actually put all the codes that we have learnt earlier in one file as a preparation for simulation later on, right? And once you have just two blocks, always block. We'll come to this statement a little later. And this is an always block which you are once again familiar with. This is just a combination realization. Whenever D1 or D2 changes, for example, if it is D1 was 0 earlier, now it changes to 1. Or let us say D2 was 1 earlier, now it changes to 0. So only in the event of change occurring, this will be processed. And you notice that we have given a name here. After begin, you are already familiar with begin and end. What has come as extra here is just a colon here and a combination circuit. That means to say whatever block that you have here, you can give a specific name and perhaps call it later on when the need arises. And that is or you can just for improving the readability, you can have this. It's a good practice to have this. And this does nothing more than take exclusive OR of two inputs as such and assign it to D, and that's what this logic is doing. This is just a D input for a flip-flop as such, and the flip-flop is written in segregated block here, which is also an always block, and action being taken at positive edge of clock. And for simplicity, I have omitted that negative edge of reset, which we had taken earlier, considered earlier. And once again, in begin and you have a begin and end. And note this once again, just as we identified this block as a combination circuit, we can identify this block as a sequential circuit. And here, what you need is whatever is the data input, we merely have to register when the positive clock occurs, edge of the clock occurs. And this also we have seen earlier. And this is nothing but an inversion of D. And if you look at the synthesis tool later on, you will see that you will be surprised.
D need not be put on the list without?
Here, no, it is already put. I am coming to that. No, not on this, because this is not an input as such. It's only an intermediate output as such. And I'll come in a minute there. So here we are inverting this D although we are inverting, actually you will be surprised in the synthesis tool to find 2 flip-flops there, not just 1 flip-flop. So our intention was just to make 1 flip-flop, and the other one is merely a inversion of this. But unfortunately, tool has not that much intelligence as such. And if you want, you will have to circumvent. As a designer, you have to know the limitations of the tool, and then find out ways and means to circumvent that those limitations. And one way to circumvent is don't put this statement here, and use an assign statement outside this here, and then say assign q underscore n equal to this, right, exclamation mark d, or you can even put tilde here, a sine wave like pattern. So coming back to this, we have not said what register is. So you notice that the outputs in this always blocks are d, q, and q underscore n. So these are all registered values. So that means, it's basically a flip-flop here. It is not really a flip-flop here in the usual sense of a sequential circuit, but still it memorizes that event, because it has to memorize, because whenever there is a change, only then we take action. So some sort of storing is taking place there. So whatever is coming in general, whatever is in output is defined in a particular block, always block. So those things you declare as a reg, as a general rule. So here it was an intermediate output, this d, which is nothing but exclusive of 2 inputs, and so you declare this d as a reg here, and that's what we have done. And naturally q and q underscore n are reg, because being the d flip-flop outputs as such. And another thing is, if you code it like this, segregating combinational or synchronous circuit, and to make it different from sequential circuit, and then it will be very easy to read your code, and you can minimize your comment writing also. So naturally that is itself a self-documenting feature here, and that is the advantage in following this RTL coding style. This is a typical model of an RTL coding. And we have also considered if statement. We revisit that one in order to see what exactly the synthesis tool maps. Say, you are all familiar with a two-way switch. You would have used a band switch in radio, or just for a short wave and medium wave. They are basically SPDT shown here, and this is single pole double throw as such. So it rests in either this position or that position in a mechanical switch as such. So this you can simulate this one, and you can get out either signal A or B in this case, depending upon this rocker as such. So this digital analogy for this is a mux, which you are already familiar, and A, B are precisely the same here, and so also the output here. And select is not apparent here, but it is the mechanical control that you have here, and that is simulated by 0 or 1. This you know anyway. 0 selects A and outputs here. Otherwise, B is output there. And if statement therefore infers a multiplexer, which we have already seen earlier, and we'll see it once again here. It is an always block, and this is a combinational circuit as such, and there's a select and A and B inputs. And suppose you want output here, which should be B. So what should you have? Select must be 1 here. Then only this B is selected. That's precisely this statement means. If select is, if you don't put equal to 1, which you can also do, it implies that it is 1. So that's a short notation, but I personally discourage this. You put double equal to, then 1 stroke B1. That will convey how many bits, and all at 1 stroke. As we said before, it should be as much self-documenting as possible, and so as to minimize your comments, and which need to be to the bare minimum, and explaining the modules rather than every statement that you have written. Right? If select is 0, it won't process this statement, and this else will take into effect. and out will be assigned A now. And notice that we have fully covered all this possibility here. The only possibility is here, select. So you have only two states. So we have covered completely here, and that's how it is basically a mux, which is precisely same here. That's what we said, that if statement normally infers a multiplexer as such. And another thing that you should not do is omit that else. In the previous example, we had an else here. If you omit that else, what happens? The tool will infer it as a latch. Latch is very detrimental because what is a latch? Basically, you have an A input to the D input, A being applied to the D input, and so long as A is varying, the output also will just follow suit. It merely is transparent so long as the clock is 0. That is, when clock is not applied, whatever is applied to A will, without any hindrance, it will appear at the output. And what will happen here? It keeps on changing here. And if you have mixed it with a synchronous circuit, it may register at the undecided point. So you should avoid this latches here. And the reason for creating a latch is you have omitted else. So next thing we are going to see is, once again already covered, it is a priority encoder as such, and this is the always block which brings out the priority encoder. First, this is given the topmost priority. For example, there are you can regard it as single 3-bit, or rather as a 3 different inputs. Base S stands for the select. So we have 3 selects here, and we have 4 inputs once again. It's also a mux basically, and you need to get either in 0 or in 1 and so on, and depending upon S2, S1 or S0 in this fashion. For example, if S2 is asserted, then what you need is at the output of the circuit, that is here, IN naught. If this is not satisfied, only then it will go to this. So not until then. So here it implies that S2 is 0. If it had come anywhere here, it implies that S2 is 0. If it is 1, it would have processed this and got out of this loop as such. And otherwise, if S1 is 1, so you assign in 1 here, and so is the case for in 2. And otherwise, here what I want to point out is, this you are already familiar. What is the point in repeating here is, so how the synthesis tool views this, and how many mux does it place. That is the pointer that we would like to show you. So here you see that the very first if statement was for S2 as such. It's here, and this is the top priority as I mentioned. So that means if S2 is 1, this input is straight away output here, right? So the gate delay here, as far as the input is concerned, it's only just from here to here. On the other hand, if you go to selection of the input 1, then it has to go through 2 mux as such in order to appear at the output. So is the case with this, and one of this will be the longest path that you will encounter, and that is how you get a priority. But the price that you are paying is 3 delays as such. 3 mux delays are coming into picture here. This is another case where redundant conditions appear, and you will have to remove that. You have to identify where the redundant case is and remove that. What is redundant, we'll have a look at this. And don't follow this type of coding, right? If you do, you will create additional mux and hence additional delay, and that in turn will slow down your frequency of operation. And how it does, let us see. This also you are familiar with the comparator we have done earlier. And if 3 numbers are there here, and basically 2 numbers are being compared, and C, D, E are outputs here. And if A is less than B, set C as the output. If it is greater than B, set D as the output. If none of this, that implies A equal to B, then do this. So what is redundant in this statement? Can you spot it out? So I'll tell you. See, A less B implies if this is not satisfied, it goes over here, then it implies that it is either equal to or greater. So this statement takes care of the next possibility, and what is left is only equal to here. So what is known? So why do you want to put another condition here, which is already known? If you put this condition, what happens? It creates one more additional mux, as we have already seen. One mux for this if statement, then else if one more mux, and one more mux here, as we had seen earlier. Precisely the same thing. So now, is there any other possibility? The solution is simple, and you can dispense with one of the muxes. So that is, this is precisely the same, and after A equal to B, D is assigned, 2 mux already present in service, and now we know that it is, when we come to this step, it is already A equal to B. So instead of putting else if, you just put else, and then what E can be straight away assigned here. And by doing so, notice that else if combined with else both means single mux only, as we have seen earlier also, and that's how we save one mux and thereby improve the speed of operation. And we have also considered case statements, and we will now see what Verilog directives are. There are basically 2 directives called full case and parallel case, and this indicates when you have a case statement here, and for the case there are, let us consider 3 bits of information, and if all the conditions are specified here, obviously it is not specified here, and you have for 3 bits you have 8 possible states as such, and 3 such states only are considered here. And what happens to the rest? When such a condition is encountered, will it be encountered? That is the first question we will have to put ourselves, and if it is encountered, we have to see remedial action for that, and for the time being we will see how this does. So there is a directive called synopsis full case, full under case. This looks like a comment, but it is a directive. It is more than a comment, right? So take care that you don't put this as any of your comments. If you do, you will get into trouble, right? What all it signifies for the synthesis tool or even a compiler is that this we have given only partial list here. We have not given the entire thing, but you regard it as a full case. That's what the implication here is. So just by giving this here, you don't have to list all the conditions, right? Is it clear to you what a full case is? Next, one more before we consider that one. Let us see what this does. See, this infers a latch for the output since all possible cases are not specified. So here, as we have seen earlier, once again 8 such possibilities are there, of which we have considered only 1 here, 1 here, 1 here, right? We have not considered 1, 1 and 1, 0, 1 and above. So we have not considered 5 different cases here, and we have not even told what to do about it. We have not put here either a full case that directive. What will happen in this case, because this is not specified and there is not even a directive, it simply infers, this tool will infer that this is a latch. That means to say, let us say it has passed through, for a particular condition, let us say it has passed through this, and it has previously stored B, let us say, because this is a although this is a combination circuit, this may be ultimately used in a sequential circuit wherein you may register, but still here also it does matter. And what will happen? So the previous value was this. So now the present case, let us say one illegal thing has come. So it is not in any of this. So it looks here. It finds no match. So what can it do? What can it infer? It will be confused. It doesn't know what to do. So what it will do is merely latch whatever was the previous signal as such. In this case, it came from B, so it continues to be in that state. And this may be detrimental for your circuit design as such. And another Verilog directive is a parallel case, which indicates that all cases listed are mutually exclusive to prevent priority encoded logic. We have seen if else if combination to be priority encoded, and case to be not priority, right? It is it appears straight away. Whatever be the condition here, it appears straight away at the output either here or here, all equally at the same time, right? So there is no nesting as such as in the case of if else if, wherein you had normally nesting takes place between mux as such, and here it straight away appears at different statements, and that here what the directive for such a case, what is mutually exclusive is, if you observe this one, this is completely different from this. See, it looks like one hot here, right, machine, and so you can see one here and then one. So all these cases are mutually exclusive, and based upon the actual input, right, you can take you can output either this pattern or this pattern depending upon the actual input themselves. That's the style adopted for synopsis parallel case. So you have to tell once again that only this mutually exclusive cases are being considered here, and if you don't put this, once again it will infer latch like the previous case. And notice that this full case and parallel case, it is not a must that you should adopt this. If you are not happy with it, you can refrain from using them and use the conventional method which has been already covered in the first, second lecture or third lectures, right? So that also we can see here. And another point about this full case and parallel case is, and this particular thing is may not this statements directives may not work in some of these systems. Maybe simplicity may not encounter one of these. I'm not sure. You'll have to experiment with it and find out. And but it is most likely that it will work in Synopsys platform, which is basically a tool for ASIC design. And so as far as possible, this full case, parallel case also you try to avoid. And in fact, you can write code, although it may be little longer code, right? But it will be safer code if you go the usual way. Now to summarize this and make a comparison between case and if else if, it is listed here. We have already seen if you want to, if your intention is to make 2-to-1 mux, use always if else statement, and if you want more than 2 inputs, you use case statement, right? And if you want priority encoders, we have already seen if else if, and you want to have a Synopsys full case or parallel case, use case here, right? And full case when not all conditions are really specified. That's what we have already covered. And regarding while writing an FSM, it's a state machine as such, and you can use case statement, which we have already seen a couple of examples before, and use case statements to describe basic state machines, finite state machines. And this also we have already seen. Synopsys parallel case to indicate mutual exclusivity, and full case when not all possible states are covered. As for instance, one hot machine, you can use this here. And don't use default unless you want a recovery state. We have, in fact, one of the examples we have considered earlier, we have used that recovery state as a default. So we took it to a safe initial state of S0 condition in while looking at an FSM earlier. And you have to be very watchful, otherwise you will be creating unintentional latches as such, which we have already considered. And therefore, in order to do this, completely specify all branches for every case. At every case statement, for every possibility, you have to give, consider it wholly. So also for if, else if statements, you have to consider all the possibilities. Don't leave anything to chance. Otherwise, you will get into trouble later on. With synthesis tool itself, it won't permit you to go beyond. And even if you wade through all the tools, finally when you make the chip, you will see that it doesn't work when you hook up the circuit. Or it may still work, and years later on, when it has reached the customer and it has been functioning, and you have changed the technology in the meanwhile, then it may malfunction. For example, the time dependent delays which we have covered earlier will be detrimental here. So similarly, completely specify all outputs for every case and if statement, We have seen this also in always block earlier using case, and we had some 8 outputs as such, D0 through D7, and we took care at every case statement that we had reset all other unwanted outputs other than the one which we wanted to set it high, right? That's what it implied here. And use full case if all desired cases have been specified. And before we wind up, let us see what is wrong with this particular example. We have an always block, and this will clear any doubts what you had earlier. And for example, you have not covered all this other cases, 5 cases here. So that is what is missing here, and this will create a latch as we have seen. And outputs are not specifically mentioned. For example, O2, O3, what will happen to these outputs is not mentioned here. So you have taken care for one output, but whatever was the earlier output, and it would continue to latch. So here also you will have a problem. So you should take care that you reset all the outputs. Either you can do it here, or you can have a statement earlier which will do reset all the outputs right on the top. And it will be better, although code is little lengthier, it may be better if you stick on here, because you can, while verifying your code, it will be easier for you. And that's what the example says. And we have one more thing before we wind up this. Let us say we want to have arithmetic operation done. Let us say a plus b plus c plus d is what we want to compute, right? You will have, and the tool will put, if you put this condition here, the synthesis tool will map it like this. It will put 3 adders as such. A plus b result will be available here. Then this will be in turn added by c with c, and that will appear here and get added in the final last adder, and finally the output will be this, right? So what is this is not a wrong thing, but you can improve this speed of processing. What will happen? You have 3 adders cascaded, so frequency operation gets hit here. And a better way to do is guide the synthesis tool, right? By putting a parenthesis here. For example, if you put parenthesis here, a plus b and c plus d here will be computed in parallel as in these 2 blocks. And then these 2 results you can once again add up here to produce the desired output, which is same as this. All that we have done is just put parenthesis here just to guide the synthesis tool, right? So with this, I will be covering RTL coding guidelines. From time to time, if you get any other new points, we will be covering up as we take up. So next what we will do is, having learned combinational, sequential and RTL guidelines as such, we will now put the combinational, sequential codes that we have put earlier as in a piecemeal manner. We will put it together as one file which will be working on these tools, which will be taking up on later sessions as such. Thank you.